So what are some examples of derived dimensions beyond just the simple areas and volumes we've been talking about so far? And this is going to give us a chance to start mixing up things like mass, time, and length together and understand how they represent what a given number means. And I want to go through that with some of the classical equations in Newtonian physics. So first of all, I want to ask the question, what are the dimensions for energy? If we use the capital E for energy as our variable, what are the dimensions of that? A lot of times we can look to the units for a hint. Well, one of the units for energy are things like joules or maybe calories. Again, this is one of those cases where the unit doesn't really tell you exactly what the fundamental dimensions are. Now, if you know what a joule is, then you might be able to get at a hint at what the dimensions of energy are. But let's not cheat. Let's think this all the way through. Well, we can work up dimensions with derivations based on the algebra of the equations that define those variables. So what's the definition of energy? Well, energy is actually a pretty abstract concept, but typically what we put it in the context of is the ability to do work. So then we can think of the dimensionality of energy as being the same as the dimensionality of work. And the definition of work is applying a force over a distance. Now we know what the dimensions of distance are, right? That's just a length. That's one of our fundamental dimensions. But now we have this new variable for force, capital F, and we have to know what the dimensions of force are before we can figure out the dimensions of energy. So again, the units for force that are sometimes used are things like newtons or pounds. Again, that doesn't really tell you directly what those dimensions might be. And we can work our way through a derivation by understanding what the definition of force is. Well, hopefully you remember this equation. It's one of the more famous equations in Newtonian physics. Force is the mass times the acceleration. It's the ability to change the momentum of a mass, and we quantify that ability by multiplying the mass times that change in velocity or that acceleration. Okay, great. We've got mass here. That's another fundamental dimension. We've got another one peeled off. We know what that is, but now we have this thing called acceleration. We don't know what that is yet, so we have to be able to figure out what this variable acceleration is in order to derive its dimensions. Well, you're probably familiar with units of acceleration that kind of directly tell you what the dimensionality is, but again, let's derive it instead of cheating. So what is the definition of acceleration? Well, it's the ability to change the momentum of something, and one of the ways to think about that is how you change its velocity. How do you change the velocity of some given mass? And we can write a differential equation to represent that. The acceleration is the change in velocity divided by the change in time, dv dt. So this is a regular differential equation, but the dimensionality of the algebra works just the same. You can just ignore those d's and not really worry about the fact this is a differential equation. You can plug in the relevant dimensions in order to derive the dimensionality of acceleration. So that means we can take the dimensions of velocity and divide them by the dimensions of time in order to come up with the dimensions of acceleration. Well, what's the dimensionality of velocity? Again, you can just look at the units here to get a hint, but let's think about it. Let's think about this one in terms of a differential equation. What's the definition of velocity? Well, one of the ways to define velocity is a change in position with a change in time, dx dt. Again, you can plug the dimensions into this, and we finally gotten our way to the point where we're two fundamental dimensions all the way, and we can just write down the dimensionality of a velocity. It's the length dx divided by time t dt. That means length per time. And we typically, with dimensional analysis, tend to write the final dimensions as exponents rather than fractions. I'm going to get into why later, but it has something to do with the order of operations being unambiguous. So most of the time in dimensional analysis, you'll see the final answers laid out in terms of exponents rather than fractions. Okay, now we have dimensions of velocity. We can plug that back into our equation for acceleration. We have length per time in the numerator, time in the denominator. The times get together, you end up with length per time squared, which is probably no surprise if you think about things like the acceleration of gravity. That's 9.8 meters per second squared. Those units line up pretty directly with the dimensions There's nothing wrong with using the units to help you check your answers. Now we have dimensions of acceleration. We can plug that into F equals ma. We can just take our fundamental dimension of mass times that dimensionality of acceleration. We get mass length per time squared. Again, if you know what a Newton is, it's a kilogram meter per second squared. So again, we can use the units to help us double check our dimensions if we happen to know what the definition of a Newton is. And finally, we can plug those dimensions of force, mass length per time squared, back into the force times distance equation for energy and work. And we can see that the dimensionality of energy is mass length squared per time squared. Again, if you know what a joule is, a kilogram meter squared per second squared, you can use that to help you double check your dimensions. So this is just an example of how all these things can be derived algebraically just by knowing some of the fundamental definitions of the variables that you're working with and knowing how to plug in the fundamental dimensions for those variables as you go. Now, we don't always break down the dimensionality of a variable into their fundamentals. If we're not talking about turning energy into motion, and we're just talking about energy moving around in a system, sometimes it's more convenient not to have to write all those m's, l's, t's, and exponents over and over again when you never really break down that energy into motion. In which case, it's perfectly valid to pick some sort of letter that represents the derived dimension and just use that consistently. So a capital E is frequently used for energy. If it's never decomposed into motion, you might see a capital F used for force, etc.